In today's video, we'll be looking at magnetic force. After watching this video, you should be able to explain how the second right-hand rule determines the direction of the magnetic force and be able to use a new magnetic force equation that we'll be introducing today. So let's get right into the action. The first thing we want to talk about is that an electric current creates a magnetic field. So a current carrying wire, there actually is a magnetic field looping around that current carrying wire. And you may remember this from a previous lesson because we learned that you can actually determine the direction of the magnetic field using the first right-hand rule. Okay, so current carrying wires create magnetic field. And this magnetic field that's being created by a current carrying wire will actually create a magnetic force on a charged particle that enters into that magnetic field. So there's a lot to wrap your mind around here, but basically if you have say two wires near each other, one wire will be creating a magnetic field and that second wire will experience a force due to the magnetic field of that first wire. Okay, that's what we're kind of talking about today. The direction of the magnetic force is important because remember, force is a vector quantity, so it's going to have a numerical value to it, which we'll get to when we get to the equation, and a direction. And so magnetic forces, basically, with magnetic forces, we're going to be working in 3 dimensions. You have the x, which typically is the horizontal, you have the y, which is the vertical, and now you have the z-axis, which is kind of like coming into and out of your screen right now. So there's a z-axis. The reason why we have to deal with these 3 dimensions is basically because force, current, and magnetic field are all perpendicular to each other. So they all work in the x, y, and z axis. So in the previous lesson, we talked about the first right-hand rule. Today we're going to introduce a second right-hand rule. The second right-hand rule is used to determine the direction of the magnetic force. So the second right-hand rule, there's a lot of different ways people will teach you how to do the second right-hand rule. As you may remember, I do not like to have your fingers or your thumb or anything moving or wrapping around. It seems like students typically make mistakes when you start moving things around. So if you have a right hand, take a look at it right now. Your fingertips, these guys right here, the fingertips are going to point in the direction of the current or a moving charge. So if I say I shoot an electron through a magnetic field, or if I shoot a proton through a magnetic field, that would be a moving charge. Or the direction of the current, which is represented by I, and a moving charge is represented by Q. The palm of your hand is in the direction of the B field. Okay, so you're going to point your fingertips in the direction of the current, and the palm of your hand will be in the direction of the magnetic field or the B field. And then your thumb, kind of looking like this, hitchhiker style, is in the direction of the force. So your hand will look kind of like this, and you're just going to move it around to make it line up with all these 3 things that we talk about. Okay, that the current is in the direction of your fingertips, the palm is in the direction of whatever the magnetic field is, and your thumb will then point in the direction of the force. Okay, practice makes perfect. When I first learned this, I was very confused, to be honest with you. So we'll definitely play around with this more and more, but this is just an introduction to the second right-hand rule. To make things even more confusing, if you have a negatively charged particle, so let's say you have an electron moving through a magnetic field, you follow all these steps that you put your fingertips in the direction of the charge or the electron, your palm in the direction of the magnetic field, and then your thumb will point in the direction of the force. The thing is since an electron is a negatively charged particle, whatever direction your thumb is pointing, so let's say it was pointing up, you would then have to flip it. So what's the opposite of up? It would be down. Or if it was right, what's the opposite of right? Left. So you have to do a little flip if it's negative. So be careful. Sometimes I'll throw in a problem or I'll have a negatively charged particle and you have to recognize that you need to flip it. So let's do some practice right now. Basically, kind of look at your screen as the surface of your screen as the X and Y axis going left and right, and then the Z is coming into and out of the page. So in this practice problem, I'm asking, what is the direction of the force? Now we're going to get a little bit artistic here. And we're going to try to draw a hand. Let me get a red color here. So what I'm going to do is I'm going to put my fingertips in the direction of the current. And so the current is like moving vertically into or vertically with the screen. Okay, so my fingertips are going to be moving vertically in the direction of the screen. So here are my fingertips. And I am not a good artist, as we can clearly see. All right, and then here's my thumb just sticking out hitchhiker style. Now, how did I know that my hand should be like this and not like this? It's really difficult to explain in terms of virtual world. The reason I have my hand like this, so like these would be my fingernails here, is because notice the B field is going into the screen, and so my palm should be facing into the screen. So I encourage you to take your right hand out. I know you're gonna look weird doing this if you watch this on your phone or your computer or whatever, but put your hand like this and you'll notice my fingertips point directly up in line with the screen, and then my palm is into the screen, like it's the B field is going through the screen. And then notice my thumb, what direction is it pointing? Well, it would be pointing left. Okay, and so the direction of the force in this case would be left. All right, let's try another practice problem. Here we have what is the direction of the force. Okay, so notice the current, this wire here, is moving from right to left. Okay, so my fingertips are probably going to be pointing left. Now, what direction should my palm be facing? Well, this circle with a dot here, here, and here represents the magnetic field. And it's saying that the magnetic field is coming out of the screen. It's kind of like hitting you in the face. Okay, so what I'm going to end up doing is when I draw my hand, my fingertips are going to be pointing in this direction. And then would my palm be facing into or out of the screen? Well, according to this, it would be out of the screen because that's the direction of the B field. Right? So my thumb would be like up here, and then here's my hand. Okay, so my fingernails wouldn't be visible at this time because it'd be like this. Okay, so notice what direction is my thumb pointing? It would be up, and so the direction of the force in this case is up. Let's take a look at another example problem one more time. So here we have a charged particle. This E with a negative sign represents an electron, and notice the electron is moving from left to right across the screen. Okay, so my fingertips are going to be pointing to the right. All right. What direction is the magnetic field? Well, in this case, it says the magnetic field is coming out of the page, So my palm of my hand is going to be facing my face, right? It's kind of actually painful to do this. It's going to look kind of like this. So sometimes it's a little painful to do the second right-hand rule, but pain is knowledge, as we like to say. All right, so I'm going to draw quickly here a right hand for you. And here we go. Now notice, oh, see, that's 3 fingers. Most people have 5, right? Yeah. There we go. All right. So notice my thumb is pointing down. So it's very common in these types of problems to say, oh, the force is down, right? Well, notice this is an electron. What type of charge does an electron have? It's negative. And if you remember a few slides ago, I said if you have a negatively charged particle, whatever direction your right hand says, you have to flip it. So instead of down, the force is actually up. Okay, and it's because you have to do a flipperoo. And I know it's like a lot of challenging tidbits to this lesson. Okay, so that takes care of the directional piece. Now remember, force is a vector, so we have a direction, which we kind of just learned by using the second right-hand rule. Now there is an equation piece, and that equation can be found right here. It looks real intimidating at first, but it's actually pretty straightforward. A lot of the problems that you'll see in this course anyway are just going to be kind of chug and plug, that you put in things you know and you solve for the unknown variable. So let's go through the variables real quickly here. F stands for force, and the force, the magnetic force in that case, is equal to B, which is the magnetic field, and that's typically measured in something called a Tesla, times the current, which is usually measured in amps, times L, which is the length of the wire in meters. So if you have a longer wire, it's going to experience more force than, say, a shorter wire. Now you have this sine piece here, the sine of theta. Why that's there is because we're only interested in the portion of the current that is perpendicular to the magnetic field. All right, so the portion of the current that's perpendicular to the magnetic field. So what that means basically is if I have a wire that's going in this direction with a current from left to right, and let's say the magnetic field is also this direction, you will say that these two lines are parallel to each other, right? Is any portion of the current perpendicular to the magnetic field? think about that for a second. Is any portion of this current perpendicular to the magnetic field? And you probably would say no. So will there be any force created? Well, according to this equation, the answer is no. How come? Well, if you put the sign of 0 in your calculator, you're going to get 0. 0 times anything is going to be 0. So we're only interested in the portion of the current that's perpendicular to the magnetic field. So to show you a problem where you would have a force, here's I, and let's say the magnetic field was vertical, or from down to up. Here you would say, oh, these are perfectly perpendicular. What is the sine of 90 degrees? Well, that's 1. Okay, so you would be experiencing the whole force. Typically in this class, you're only going to see problems where sine is either 0 or sine is 90. If you take physics in college or whatever, they'll start making these not 0 or 90. They'll be at different angles of 47 degrees or what have you. But typically in this class, unless it's maybe an extra credit problem, you only will see sine of 0 and sine of 90. And so you almost in a way can not worry about this component, because it's either going to be 0 here or it's going to be 1. And 1 times anything is whatever, and 0 times anything is 0. Okay? All right, let's move on. There's one more equation, because you'll notice in the beginning of this lesson we said that a current-carrying wire can experience a magnetic force and a charged particle can experience a magnetic force. So here's the equation for a charged particle. F equals Q, which if you think back to static electricity, what does Q mean? Q is the charge on a particle in coulombs. Okay, so we're going to be measuring it in coulombs, times V, which stands for the speed of the particle in meters per second, times B, which is the magnetic field measured in the Tesla, times the sine of theta. Again, it's the same exact reasoning why you have that sign there as in the previous slide. Basically, we're only interested in the component of the particle that's traveling perpendicular to the magnetic field. So if the particle and the magnetic field are parallel to each other, you'll have no force. Okay, they have to be perpendicular to each other. So kind of keep that equation in mind. You'll probably see some problems where you're using this. Let's take a look at an example problem. This would be totally fair game to get, say, like on homework or a test or what have you. A wire carrying 15 amps of current has a length of 25 centimeters and a magnetic field of 0.85 T. T stands for Tesla. Find the force on the wire when it makes the following angles with the magnetic field. Okay, so I have two scenarios. One when it's 90 degrees and one when it's 0 degrees. Our equation that we're going to use is F equals, I just remember Bill, times the sine of theta. Bill sine theta. So let's just plug in things we know. A current carrying wire of 15 amps. So that's I, 15 amps. All right, cool. Has a current with a length of 25 centimeters. Notice this is trying to trick you. They have it in centimeters. We can't use centimeters in this equation. We have to change this to meters. So basically you're going to divide by 100. It is 0.25 meters. In a magnetic field of 0.85 Tesla. So B is 0.85 Tesla. And it makes the following angle, 90 degrees. So I'm going to have sine of 90, which if you throw it in your calculator, that's actually 1. Okay, so it's just times 1, so you almost can ignore that term right now. So here we go. What's F? Okay, so 0.85 times 15 times 0.25 times the sine of 90. If you throw that in your calculator, you're going to get a force of 3.2 newtons. All right, that would be the answer. So hopefully you'll see like this is just kind of plugging numbers in a calculator. You do have to kind of check yourself in terms of centimeters and all that, but you're just kind of throwing numbers in a calculator. Now they're wondering, well, let's say the wire and the magnetic field make an angle of 0 degrees. What would the force be then? Well, if you kind of think about what the sine of 0 is, the sine of 0 is 0. So anything times 0 is going to be 0. And so the force in this case turns out to be 0 newtons. That almost looks like 6, but it's actually 0. Let me fix that. So if you can catch that, that's helpful in terms of plugging all this stuff in to then realize, oh, it's 0. But if not, that's okay. I encourage you to just write all this out, and if you get 0, then say, oh dang, I could have caught that, but that's all right. That actually takes care of this video. I will see you guys next time.